All right, mean value theorem. Previously in Rolle's theorem, we had f of a equaled f of b, which meant the slope m equal, y2 minus y1 over x2 minus x1. Because these are the points a comma f of a and b comma f of b. We have f of b minus f of a over b minus a. That equals 0, and that equaled f prime of c. Mean value theorem is a much more general version of the Rolle's theorem where we don't make that happen. It doesn't have to equal 0. So let's take a look at how that works out. If f of a doesn't equal f of b, then f of b minus f of a over b minus a doesn't equal 0. So this happens when the slope isn't 0. So we'll have the slope is some slope m. We don't know what the slope is, it's m. But that means there's also will be a c where f prime of c equals m. And taking a look at it pictorially, let's say our blue line is our function, and I've got a f of a listed. That's a f of a right there. Here is b f of b right there. And we find the slope. That slope equals m. There are two other points on this graph that have a tangent line with the same slope, which means the derivative is the same as that m. And it's guaranteed to exist. There's at least going to be one, as long as it's continuous, differentiable, and stuff like that. So let's look at the mean value theorem. F of x is continuous on a closed AB and differentiable on an open AB. There exists at least one point where x equals c in the interval AB, such that f prime of c equals f of b minus f of a. The proof of this involves using the Rolle's theorem. Let's take a look at it. We're going to consider this line here from a f of a to b f of b. This line right here. We're going to look at that line. We are going to make a new function that does the vertical distance between our line and some other line. Okay? That's pictorially what we're going to do. I'll show, I got a better picture down below. We've got some line from a f of a to b f of b where the slope is m. And so the equation of the line between those 2 points, this line right here, has this equation right here. We plug in a f of a and we get that. Okay? So I solve for y. I've got y equals f of b minus f of a over b minus a. That's just a big fat m right there. Big fat m. This is like my x minus x naught. And this is my y naught. Okay? So we make another function called g of x. And g of x is going to represent that vertical distance right there. It's the vertical distances. And vertical distance is y2 minus y1. That's a vertical distance. So what we're going to do is we call the point on the line on our y equals f of x, x f of x, and our g of x will use some xy. Okay? So I've got x f of x, that's my y2. That doesn't highlight very well with the purple. And that doesn't do very well with that one. Not highlighting very well. Y2 is my x f of x, y1 is xy. So g of x is y2 minus y1. Like I said, we're doing the vertical distance. So I just plug those in. Y2 was f of x, and y1 was y. But y is this, okay? So we plug those in. I get f of x from here minus the y from up here. It's kind of funky looking, right? But check this out. If we plug in a, g of a is f of a minus that big old y thing with a plugged in. F of b minus f of a over b minus a times a minus a plus f of a. A minus a is 0, which makes this whole thing right here 0. And all I've got left inside the bracket is 0 plus f of a. So when I do the subtraction, I've got f of a minus f of a is 0. Then we do it with b. If I plug in b for x, we're filling in our x's here. I fill in my x's, f of b. Notice that this b minus a cancels out that b minus a. So I have a b minus f of b minus f of a on top, plus another f of a, as we see over here. I'll highlight it underneath like that. That's better. And you'll notice that these two cancel. Minus f of a plus f of a cancel. So we've got f of b minus f of b. That equals 0. So both g of a and g of b equal 0. And g of x was continuous and differentiable on ab. So g prime of c equals 0 for some x equals c inside of ab. That's Rolle's theorem. So let's go back and look at g of x. We had g of x up here. We're going to take the derivative of that. And the derivative only hits the stuff with the x. Okay? So if I take the derivative of that, I get that. The derivative of that is f prime of x. This is just some number. Okay? And when we take the derivative of this, that's just 1. The derivative of that is 0. So we just get f prime of x minus our slope. Oop. Remember, that's our slope. M. So now we plug in c. We're looking for this c right here. We plug it in. G prime of c equals f prime of c minus that slope. That has to equal 0 by Rolle's theorem. We're applying Rolle's theorem now. And we will add f of b minus f of a over b minus a to both sides. And we get f prime of c equals f of b minus f of a over b minus a. That was MVT right there. And when you see a little box like this, or QED, this means proof is done. It signifies a conclusion of the proof. QED means, I think it's pronounced quod erat demonstrandum, which means it's Latin for which was to be demonstrated. So we showed what we needed, and this was to be demonstrated, and we did demonstrate it. So that's the proof of the mean value theorem. And now that wasn't all that exciting, but it does show how it works. It's the Rolle's theorem generalized. Let's do another video for our examples.